Hi everyone, today a video on alcohols and in particular an introduction to them and ethanol production. So alcohols have the functional group OH. They have a hydroxyl group attached to the hydrocarbon chain and they're pretty reactive. And so the general formula for an alcohol is CnH2n plus 1 OH. So we've taken an alkane skeleton and we've replaced one of the hydrogen atoms with an OH group. And this is often just shortened straight down to ROH, where the R represents the alkyl chain. Now the COH bond angle is around about 105 degrees, and this is because the 109.5 degree angle of a perfect tetrahedron is essentially sort of squeezed down by the presence of lone pairs. So if we look at the oxygen in an alcohol, we have one bond to carbon, one bond to hydrogen, and then we have two lone pairs. So the pseudostructure of this is tetrahedral. There are 4 pairs of electrons. We know the bond angle is 109.5, but we also know that as we change from bonding pairs to lone pairs, that lone pairs repel more than bonding pairs do. And so the angle you can see in ammonia with one lone pair, 107, in the alcohol, roughly 105. And we have this idea that for every bonding pair that turns to a lone pair, we reduce the angle by about 2 degrees, or 2.5 degrees. So when we go about naming alcohols, we use the suffix ol to represent that it's an alcohol. If there are other functional groups present though that take priority, we use a prefix, hydroxy, instead. Now, the standard IUPAC rules for naming apply here, so we have to always look for our longest carbon chain. We need to number the position of our alcohol group. We always want the numbering to be the lowest possible. If there's multiple of the OH group, or if there's multiple of any substituent, we have to use di, tri, tetra to say how many there are. We must number everything in the molecule, and remember that we always name things in alphabetical order, not numerical order. So the examples shown here, we have propan-1-ol. We have a 3 carbon chain, so it's based on a propyl length chain. We have our OH group, so it's an alcohol, so ol, there's no other functional groups. And we could say that it's on the carbon number 3, or that it's on carbon number 1, and we want the lowest possible numbering, so it's propan-1-ol. We essentially take the length, which is propane, and we knock off the E, so it's propan-1-ol, there's no E. Likewise, if we have a position isomer of this, we've moved the OH group to the 2nd carbon. This is now propan-2-ol. The third example contains a CN group. This is a nitrile group, and this actually takes priority in naming. So now we don't use the suffix ol, but the prefix hydroxy instead. We look for our longest carbon chain, which is 3 carbons long. And then we have to number our substituents. We have our 3 carbon long chain. We have 2 methyl groups coming off the 2nd carbon that aren't part of the main chain. And we have our OH group coming off our 3rd carbon. Now we could name it as the carbon that the OH is on as being the 1st carbon, but again the cyanide group, the CN group, takes the priority here in naming, and so that carbon in the CN group is the 1st carbon. And remember that we name in terms of alphabetical first rather than numerical, so the name of this is 3-hydroxy 2,2-dimethyl propane nitrile. Now for nitriles we do keep the E, so it's propane nitrile. Notice how as well that when we number, we have to number every single thing, so it's not just 2-dimethyl but 2,2-dimethyl, because there are 2 methyl groups. And then finally at the end we have an example where we have multiple OH groups. There's no other functional group, so it's named using ol. It's on carbons number 1 and 3. Again, it could be 2 and 4, but we want the lowest numbers, so 1 and 3. And it's a chain length of 4 carbons, so this would be known as butane 1,3-diol. Now a bit of kind of naming grammar almost. If the suffix that we're dealing with starts with a consonant, or we have multiple of the functional group, we keep the E in the name. So that's why it's propan-1-ol and propan-2-ol, but propane nitrile because it starts with a consonant, or butane 1,3-diol because we have multiple, so butane rather than butan. So how do we classify alcohols? Well, we classify alcohols by how many other carbon-based groups are attached to the carbon that has the OH group on. And we classify them as either being primary, secondary, or tertiary. So the primary alcohol, we have our COH bond, and that carbon atom is attached to one other carbon group, denoted as R in this case. Secondary alcohol has the carbon OH bond, with that carbon being bonded to two other R groups, two other carbon-based groups. And a tertiary alcohol has three other carbon-based groups bonded to that carbon with the OH on. Another way to think of it is that primary alcohol is where the OH is at the end of a chain, a secondary alcohol is where the OH is in the body of the chain, and a tertiary alcohol is where the OH is at the branch of a chain. But the actual technical definition is to do with how many carbon groups are attached. So in terms of physical properties, the OH group in alcohols means that we have hydrogen bonding occurring between molecules. So not only do we have van der Waals forces that interact between all molecules, we also have dipole-dipole forces in operation because we have polar CO and OH bonds. The C is delta positive, the O delta negative, the H delta positive due to the electronegativity of oxygen. And we have hydrogen bonding. Remember that hydrogen bonding has to occur between something that contains fluorine, oxygen, or nitrogen, along with hydrogens that are bonded to those. So alcohols therefore have higher melting and boiling points than alkanes of a similar molecular mass because they have these extra intermolecular forces. Now, hydrogen bonding also makes the shorter chain alcohols soluble in water because the hydrogen bonds can form between the OH group of the alcohol and the water molecules, but it's very dependent on how big the alcohol is. So the smaller chain alcohols, because an alcohol is made up of our polar OH bond and our non-polar alkyl chain, if that alkyl chain becomes very, very large, then the non-polar part of that molecule dominates and it wouldn't be soluble in water. And if you're ever asked to show the hydrogen bonding, make sure you draw at least two molecules to be able to show the hydrogen bonding. Dashed line between the oxygen on one and the hydrogen on another molecule. Make sure you show it starting from the lone pair on the oxygen, ending at the hydrogen atom, and make sure you show your partial positive charges and your partial negative charges. So, ethanol is probably the most widely known and important alcohol. It's obviously very widely known from being used in alcoholic drinks. But alcohols in general are very important in industrial chemistry because they are often used as intermediates to other chemicals. Alcohols are pretty easily synthesized and they're very readily converted into other compounds, so they have a lot of synthetic potential to make lots of different compounds. Now, methanol is also an important alcohol, and methanol is made from methane, which we get from natural gas, and this is increasingly being used as a starting material to make other organic chemicals. Ethanol, industrially, is made by reacting ethene, the alkene, which we get from cracking crude oil, with steam. Now, we take the steam and the alkene and we use a phosphoric acid catalyst, H3PO4. Essentially, it's just an acid catalyst. Now, the main source of ethene comes from ethane, from natural gas, but some of it also comes from the naphtha faction. It's also made from sugars by fermentation as well, which is how we get it in alcoholic drinks. So ethanol, as I said, is very important. It's used as an intermediate in the manufacture of lots of organic chemicals. It's often used as a solvent in cosmetics as well, and in the manufacture of lots of drugs and detergents. And so this reaction of taking ethene to ethanol through steam and the phosphoric acid catalyst is called a hydration reaction. We can think of it hydrating the alkene with added water across the double bond. So the mechanism for how this works, this is an electrophilic addition reaction. Our alkene is acting as a nucleophile. It's a region of electron density. We have that pi bond, which is a region of high electron density, able to act as the nucleophile, the lone pair, the electron pair donor. Water, in this case, actually acts as the electrophile. And so this is an electrophilic addition. We are adding an electrophile across the double bond. And so the mechanism for this is as follows. The reason why we have the acid catalyst is to make the water into an electrophile. Water on its own isn't a particularly good electrophile. In fact, it acts more often as a nucleophile. And so to turn it into an electrophile, we have to protonate the water. Now, if you've seen the acids and bases videos, you'll know that H plus never exists just as H plus, it always exists as H3O plus, always coordinated to a water molecule through a dative covalent bond. So the reason that we have our acid catalyst there is to turn our H2O into H3O plus. This is then a very electrophilic molecule and can be attacked by our nucleophilic alkene. So we draw an arrow that starts from our region of electron density, the double bond on the alkene, and we draw it to the hydrogen. We don't draw it to the oxygen, even though it's got a positive charge on. And the reason for this is because the oxygen, what I've not shown in this mechanism here, is the oxygen also has a lone pair. The oxygen has 8 electrons. There's no empty orbitals to be able to attack into. It already has 8 electrons. We can't make another bond to it. So instead, we attack one of the hydrogen atoms that is attached. That's our end of our arrow. And then the second arrow starts from the HO bond and ends up at the oxygen. It's quite often that arrows will start at bonds and end up at electronegative atoms because they're able to take the electron density. So in doing that first step, what happens is we turn our H3O plus back into H2O, normal water. But remember that whenever we draw a mechanism, every step has to balance in terms of charge and in terms of the atoms. So we started off with a positive charge overall. We have to have a positive charge somewhere. It's not on the water this time. And in fact, the positive charge is now on our organic molecule. In breaking open the double bond, we've added that hydrogen atom to one of the carbons. The other carbon, though, has been left unsaturated without the maximum number of bonds it can have. And we've actually created a carbocation. Positive charge now on the carbon. And carbocations are planar molecules, trigonal planar molecules. So our second step in this is a very simple arrow. It goes from one of the lone pairs on the oxygen, that's our nucleophilic reagent here, to the positive charge on the carbon. Now this one is correct because the carbon only has 6 valence electrons. It doesn't have the maximum number of electrons, so we can directly attack that carbon atom. And that's our electrophilic addition mechanism. The only step we have at the end, we said that our catalyst with acid, the key thing being catalyst, it must be regenerated. And so by adding water, H2O, to that carbocation, we now have an oxygen that has 3 bonds to it. Again, we have to balance in terms of charge. So the positive charge here is on the oxygen atom, and so simply we lose an H plus ion. So we have an arrow that starts from an OH bond and again ends up on the electronegative oxygen atom. We've regenerated our catalyst, our H plus, and we've formed our alcohol. We've turned an alkene into an alcohol through an electrophilic addition reaction. So another way to make ethanol is through fermentation. And so during fermentation, carbohydrates from plants are broken down into sugars and then converted into ethanol by the action of enzymes from yeast. And so the carbohydrates come from crops such as sugarcane. And the key step in the breakdown of this sugar is the process called anaerobic respiration. That means without oxygen. And so the glucose, C6H12O6, essentially sugar, gets broken down from the enzymes from within yeast, and it produces ethanol, C2H5OH, and carbon dioxide, CO2. Remember, this is a chemical equation, so we have to balance this as well. 2 lots of ethanol and 2 lots of carbon dioxide. Now, the rate of this reaction is affected by temperature. Like most reactions, it's slow at low temperatures and much faster at higher temperatures. But the issue is that we also have enzymes, and enzymes are often made ineffective or denatured by high temperatures. It means that they don't work as well anymore, even at all. And so a compromised temperature of 35 degrees Celsius is used. It's warm enough that the rate of reaction isn't too slow, but not so hot that it starts to denature the enzymes and stop the reaction from working at all. The reason why it's anaerobic respiration as opposed to aerobic respiration, where we have oxygen, the reason why we keep the oxygen in the air out of the reaction vessel is because we don't want to oxidize the ethanol to ethanoic acid. And we'll see in some other videos when we look at carbonyl chemistry and later on with alcohol chemistry that alcohols are very readily oxidized up to aldehydes, ketones, and even carboxylic acids. So it's important to keep the air out of this if you want to stick to the alcohol. Now, once the fermenting solution contains about 15% ethanol, the enzymes unfortunately are unable to function any longer and the fermentation stops. And so the way to get your ethanol out of this mixture is to distill it by fractional distillation. Now, ethanol, the use for it is to be used as a motor fuel. It's quite often mixed in with petrol. But the problem is that the ethanol that is made from ethene is not a renewable resource because the ethene comes from crude oil, which is a non-renewable resource. Another thing is that carbon-based fuels are contributing to global warming and climate change, since the burning of the carbon-based fuels produces carbon dioxide, a greenhouse gas. However, since the ethanol produced by fermentation is made from renewable crops, this is a renewable resource. This is an example of something that we call a biofuel. So a biofuel is a fuel that is derived or produced from renewable biological sources. Now, when this ethanol is actually burnt as a fuel, as we'll see on the next slide, the exact same amount of CO2 is returned to the atmosphere as was originally locked up in the crop. So while we're releasing CO2 by burning this ethanol, we've actually taken in the CO2 at the start. So the overall CO2 net production is zero. We talk about this thing being carbon neutral. It's not produced any more CO2 than it took in the first place. Now, the crude oil, as we said, the non-renewable resource, how do we get the ethene from the crude oil? Well, we crack it and we dehydrate. Sometimes we dehydrate to get down to the ethene. The rate of reaction, though, is very quick, and it can be done through a continuous process, and the purity of it is essentially pure. However, when we use carbohydrates, the sugars in this renewable process for making ethanol, how do we make it? Well, we make it through fermentation and distillation. However, the rate of reaction is slower. We have to do it in batch process rather than continuous, so you can't make as much as quickly. And the purity of it isn't as great. It's formed as an aqueous solution of ethanol, so that's why we have to distill it. It's often impure. So while it comes from a renewable resource, there's still steps that need to be taken in terms of getting faster rates of reaction, getting the processes to be more efficient and the purity to be better. Another thing is it doesn't take into account any other carbon costs, such as energy needed to transport the crops and the fuel or to process the crops as well. So it's a bit of a kind of tunnel vision of these processes. So as I said on the previous slide, the ethanol that we make by fermentation is sometimes called a carbon neutral fuel. And so I said that there was no net production of CO2. The carbon dioxide that you release into the atmosphere when this ethanol is burnt is balanced completely by the carbon dioxide that was absorbed during photosynthesis. So the photosynthesis, remember, takes water and carbon dioxide and converts it into glucose and oxygen. The key thing here is that we have our 6 moles of water plus 6 moles of CO2, giving our glucose C6H12O6 and 6 moles of oxygen. So in total, we've absorbed 6 moles of CO2 for a mole of glucose. Then when we ferment 1 mole of glucose, that produces 2 lots of ethanol and 2 lots of CO2. And then those two ethanols, which have come from the 1 mole of glucose, get combusted. And once you balance that equation, produce CO2 and water, but you produce 4 moles of CO2. So in total, during the fermentation and the combustion, we've released 6 moles of CO2. So we've taken in 6, we've released 6, hence it's carbon neutral. So at present, we take crude oil. From that crude oil, we get ethene. We convert that ethene to ethanol. We also can make polyethylene, the polymer, and many other useful chemicals. But the key thing is it comes from this non-renewable crude oil. In the future, we're hoping that we can take this renewable resource of the carbohydrates and the sugars, convert it to ethanol through fermentation, and then convert to ethene quite often through a dehydration reaction. And ethene can be converted into polyethylene and many other useful chemicals. So the key thing being that we can get to ethene, we can get to ethanol, but from a renewable resource. So time to have a go at some questions. We have the first question, naming the alcohols, then to give a chain position and functional group isomer of pentan-1-ol, and then a question about whether pentanol is water soluble versus methanol. So if you'd like to have a go, pause the video and the answers will be on the next slide. So the naming of the two compounds, the first one, remember the first thing we always do is look for our longest carbon chain. Our longest carbon chain is 3 carbons long here. So we're going to be based off a propyl chain. We then need to look at our substituents. So we have on the second carbon a methyl group. We also on the second carbon have a bromine group. And then again we could put the OH group on the third carbon or the OH group on the first carbon, depending on whether we number from left to right or right to left. We always want the lowest number possible, so it goes on the first carbon. So the ending of it is going to be propan-1-ol, but not propane, but propan-1-ol. And then we have to put our substituents in, remembering that we always put them in alphabetical order. So this is known as 2-bromo, 2-methyl, propan-1-ol. A second example here is a diol. There's 2 OH groups here. No other functional groups, so we can still use the suffix ol. There's 2 of them, so di, and we have to number them. One's on carbon number 1, one's on carbon number 2, so 1,2 diol. And then finally it's 2 carbons long, so it's based off an ethane chain. So this is known as ethane 1,2 diol. And the really important thing here is that it's ethane, not ethan, because we have multiple of the alcohol groups, and if we have multiple of the functional group, we have to keep the E on the end of the name. So ethane 1,2 diol. Then we're asked to give a position, chain, and functional group isomer of pentan-1-ol. The position isomer is very easy to do. It's simply moving the functional group. So rather than pentan-1-ol, we can have pentan-2-ol with it on the second carbon. The chain isomer, we now need to essentially make the chain a bit shorter and put one of the carbon groups out of the chain, branching out of the chain, so it becomes a substituent. And so easiest way to do that is kind of the carbon before the end of the molecule. Take it from being at the very end of the molecule to being on the penultimate carbon. Now our longest chain is only 4 carbons long, and we have a methyl group on the third carbon along. So this is 3-methyl-butan-2-ol. And a functional group isomer. Remember, a functional group, we have to have the same formula, but a different functional group present. And the functional group type that matches this is something called an ether. This is where we have an oxygen somewhere in the middle of the molecule with carbon groups on either side. And so this is actually known as methoxybutane, CH3, CH2, 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 O, CH3. And then finally the question asking whether pentanol versus methanol was soluble in water. Well, pentanol actually isn't soluble in water. The reason, as we said, we have our polar OH bond. We can also make hydrogen bonds as well as dipole-dipole forces that are going to help with the solubility. However, the alcohol chain is non-polar and therefore is not going to mix with water, and it's depending on the size of that alcohol chain. So for pentanol, the alcohol chain is quite large, and therefore it ends up being overall a non-polar molecule, and so it doesn't mix with water. The ethanol, much shorter carbon chain, and therefore the molecule is much more polar overall, and therefore the strong hydrogen bonding can occur with water to make it soluble. So thank you for watching. You can find more videos like this on my YouTube channel. If you found this video helpful, please consider leaving a review on one of the tuition websites. I offer tuition for chemistry. Please check out my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, always feel free to drop me an email. I'll be happy to help.